Canal com a sua proposta aqui, ou os aniversários ou o chocolate.
Maria, boy. Caralho, o cara extremamente, como é que se diz? Capitalista.
Isso está no YouTube.
Mas é preto no branco, né?
Good afternoon, guys. Today, Heitor and Mikael will talk about what is an abelian and a non-abelian group. So let's start.
So, hello everyone. Good afternoon. Today, I'm going to talk about what is an abelian group, and more importantly, why does that matter? Let me just set the time. I forgot the time. Okay, I'm going to talk about what is an abelian group and why does that matter for us particle physicists. So first, what do I mean when I say group? Group is nothing but the main subject of group theory. That is a branch of mathematics that study groups. And a group is nothing but a set. Here is denoted big G, and a particular operation. Here is denoted star. And what happens is the elements of this set are, I can take this operation and operate the elements of the set with each other. And a group must have some certain 4 specific properties. That first, they must be closed so that when I operate 2 elements of the set, it returns to me another element of the set. So it is closed. And the operation must be associative. That's just some detail that says that if I have A, B, and C in this set, and if I operate A with B and then with C, it gives me the same thing as if I operate B and C and then operate with A. That's just a property. And there must be a neutral element, that is an element that when I operate this neutral element with some element A, I return just the element A. And I must have a inverse element. That is, when I multiply, let's say, A with the inverse of A, it returns to me the neutral element that I define in the third property. And that's it, just the formal way of defining a group. So let's illustrate this better with the symmetries of a equilateral triangle, because group theory is extremely related with symmetry, with transformations of symmetry. And here to illustrate this, I have 6 possible transformations that preserve the symmetry of an equilateral triangle. What do I mean by that? When I perform these 6 operations, the triangle is the same as when I started. So the initial orientation is alpha, and when I perform the first operation, that's just the identity operation, the neutral element is I do nothing with the triangle, and the vertices A, B, and C stay in the same place. The triangle stays the same way, and the symmetry is so preserved. And I can do also 2 different kinds of rotations, one with 120 degrees of rotation, and that returns me, again, the same triangle, like in the same way that it started, that's alpha. And I have the 240 degrees rotation, that is, I rotate like 2 times, and again, the symmetry is preserved. And I have 3 different axes of reflection that I can reflect upon and still preserve the symmetry. I have the vertical one that's illustrated in the orientation delta. And when I perform the reflection transformation, I have the symmetry, and I have that the point A stays in the same place, and I change B with C. And so in this group that I call the dihedral group, and is represented by D3, I have that each transformation corresponds to an element of the set. So the 6 elements are just matrices that will perform the transformations that I want of symmetry in the triangle. So the transformations are matrices, and the operation of the group is just the matrix product. That is what happens if I perform two different operations successfully. So it's the same that if I apply C to the triangle and then apply B, let's illustrate that. C and B are the rotation. So if I apply C and then apply B, it's the same that I take these two matrices, C and B, and I perform the product between them. So that's just the operation of the group, to be formal in the definitions. And what I want to investigate is what happens if I change the order in which I do these transformations. In this example, I apply D and then B in the left, because we read from right to left. And so in the first one, I start with alpha again, and I apply D, that is a reflection. I reflect it, I have delta orientation, and then I apply B, the rotation. So I end up with the zeta orientation. If I do the same thing, but with the order, with inverse order, that is, I apply the rotation B and then the reflection D, I end up with the epsilon orientation. So although the symmetry is preserved in both ways, the final result of the orientation is different. So at the end of the day, what I want to say is that the order in which I perform these transformations of symmetry matter. I do not end up in the exact same place if I just change the order. So if we organize that in a table, that is, how do I read this? You take the first column and you operate with the first line of this table. So in that example, I had, let's say I start with D in the triangle, the transformation D, and then I perform the operation B, I end up with E. And if I do the inverse, I start with B, and then I perform D, I have F. It's the same as I apply the F transformation. So as we can see, this group in total, it doesn't have the commutative property that I'm looking for. It just have this property if I look to these three first operations, A, B, and C, the identity and the two rotations. So if I just look at the subgroup of this dihedral group, I see that only the rotation transformations are indeed commutative. And so I can say that this subgroup is an abelian subgroup. That's how we name it. That's an abelian group, subgroup in this case. And because the order doesn't matter, if I apply, let's say, the transformation B and then the transformation C, it is the same if I apply the inverse, the transformation C and then transformation B. I end up in the same place in the table. You can see that the table is symmetric through this diagonal, this main diagonal. I have B here, I have B here, C, C, and so on. So that is the answer. This is an abelian group. Is a group that the elements of the set of the group have this commutation property. It doesn't matter the order. But why all of this matter, why I'm talking about triangles and symmetry group theory, is because the standard model of particle physics is based in the symmetries of the quantum fields of the particles. And each symmetry, each local gauge symmetry of the fields gives me an interaction of the standard model. So I have these three groups that compose the standard model. We have U1, that is the group that gives me the symmetry of electromagnetism. We have SU2, that in the same way is a group that gives me the symmetry of the weak force, and SU3 that in the same way gives me the strong force. And from all of these three groups, the only abelian one is U1. So electromagnetism is the only interaction that comes from a abelian group symmetry. And that's what I'm going to focus. Mikhail is going to talk a little more about the SU2 symmetry, because it is a non-abelian, but I'm going to focus in electromagnetism. And this U1, U stands for unitary group, meaning that each matrix of transformation, that group must follow this property. that is the A dagger. A is the same as A dagger. That is the identity. It's just the property that defines not only U1, but all of them, because the U here is special group, special unitary group 2, that is just the dimension that changes. This number actually tells me the dimension of the matrices of the group. In U1, I have just one dimension. So a matrix of one dimension is just a number. A matrix of dimension 2 is a square matrix of 2 and 2, 2 by 2, 3 by 3, and so on. And the main implication of the U1 group being abelian is that the electromagnetism that is associated with U1 is that the boson of the electromagnetism has no electric charge. That is, there's no interaction between photon and photon. Here in the picture, you can see that light doesn't interact with light. Photon doesn't interact with photon because of the abelian property of the group U1. That doesn't seem as intuitive, but if we take the steps, if we redo the steps to reach quantum electrodynamics, we can see this more clearly in the final Lagrangian. So quantum electrodynamics is just based on this transformation of rotation, because U1 is nothing but the symmetry of transformations of a circle. So if I have this blue circle, I know that I can rotate it by an infinite amount of angles continuously and still maintain the symmetry of the circle. That is the symmetry of U1 geometrically. So what I do is I perform a rotation on a fermion field, a psi field like this, and the rotation must be a function of space-time because it is a local symmetry. It just tells me that it is a function of space-time. And that's it. I'm going to investigate what happens when I do this transformation to the field, and I get that the Dirac Lagrangian now is different. It has an extra term like this, so I want to cancel it out. So the Lagrangian is invariant under this rotation transformation. To do so, I have to introduce an extra field, an outside field, vector field, that is this A mu, that is a vector field that comes to compensate the transformation. In which way? I have to substitute the derivative like this and add the field, and this vector field, this new vector field, also transforms with the gauge that I originally applied to the psi field. And if I do that in this way specifically, the Lagrangian is now invariant under this transformation, and I get the QED Lagrangian. That is, what is this? It's just the Dirac Lagrangian here, the first two terms. It's two terms, the kinetic and mass term for the fermion, and the kinetic term for a photon. I just added here because in the middle, I have the interaction term between a fermion and a photon. I have here the field of a fermion, the psi, and the field of the photon, that is a mu. And this guy, the Q that comes from the transformation here, as I defined, is nothing but the coupling constant between these two fields. So how strong the fermion field couples with the photon field depends on the charge of the fermion. That is pretty intuitive. And in the end of the day, all of this Lagrangian is saying is how a free fermion behaves, how a free photon behaves, and how the two couple with each other, how they interact with each other. That is nothing but electromagnetism. And as we can see, there's no term of self-interaction of the photon. There's no a mu term of interaction because electromagnetism comes from an abelian group, as I say here. As we have an abelian theory of electromagnetism, there's no term of interaction between photon and photon. Photon just interacts with what the photon just interacts with particles that have charge. And as the photon doesn't interact with itself, it doesn't have charge. And the conclusion is that QED, that I've just derived in pretty fast, but it is really much easier to derive QED than the other two interactions of the standard model, because the electromagnetism, as I said, is based on a abelian symmetry group, and abelian groups are much easier to deal with than non-abelian. And also this group U1 of electromagnetism has only one generator. That what exactly is a generator is the topic that Mikhail will talk more about. But basically every group has associated with a number of generators, and U1 has only one generator. So that physically implies that the interaction of U1 will have only one boson. And in that way, the SU2, that's the group from weak force, have two generators. So we have, no, sorry, it has three generators. So the weak force has three bosons and so on. But the thing is, the generators for weak and strong force are non-commutative because they are based on non-abelian theories. And that's the main conclusion, that the number of generators correspond to the number of bosons of a interaction. And here the picture is just to show that, again, photon doesn't interact with itself. The W boson that carries electric charge because of the non-abelian character of this interaction, you can see that the W boson interact with itself, and the gluon also interact with itself because also comes from a non-abelian theory. And here is just an example of the weak force transformation. That here we have T, that are the generators of the weak force that multiplies the boson. Here we're going to have the W plus W minus and Z bosons. And just to illustrate how much complex it becomes, because the generators of the SU2 group are 2x2 matrices, and it becomes a more complex algebra to deal with. And that's the main conclusion. Abelian groups are much more easier to work with. And I hope I have answered the main question of the presentation. That's it. Thank you for your attention.
Nice presentation. Just a small comment. This is much more of a technical comment on something you have said, which is you said that when you show the symmetry of the standard model, SU3, SU2, U1, you specified saying that U1 is electromagnetism and that SU2 is weak interaction. But the most correct way to point out is that SU2 cross U1 actually generates electromagnetism and the force separate, okay? Because both of them come from there. And so that specific covariant derivative you've pointed out for the SU2
at the end,
that W there, more specifically, wouldn't be the W plus, W minus, and the Z boson. They would be the three generators coming from the SU2, which will in turn become with the U1 the bosons for electrons.
That's exactly the question.
It's more of a comment on, because it's more a technical comment. When you present that again, mostly probably in your thesis, PCC, you don't repeat it because it's important that you understand that.
I have to show the derivative transformation for the electroweak.
No, you don't have to show it. I'm just saying that you cannot say that SU2 is what brings out the weak force by itself. Because, for example, the Z boson, I think he will show it, is a mixture between boson from the SU2 and a boson from the one.
That's exactly the question that I have, because, for example, this imaging is very, I mean, when you put it, you have to wait for a lot of questions on my side of this. So, for example, you said that the non-abelian bosons, they interact with themselves. They interact because they are non-abelian, blah, blah. So, but in the case of the Z, why it doesn't interact with itself?
Yeah, it doesn't carry charge.
Yeah, but that's the point. It's not a weak boson. It just has to carry electric charge.
That's
What's the charge of the weak force?
It's just the electric charge because the weak force was unified with electromagnetism. They come from the electroweak symmetry, that is SU2 U1.
The answer exactly relies on what Zell was talking about, because there is a mixing between both groups. So for the case of the W plus and minus, it will be a mixture of two bosons in the weak, let's say in the
of
U2
the electroweak.
the U2 SU2 left symmetry. So these two will be like a ladder operator, but in the case of Z, it will be a mixture between the W3 and the B that comes from U1 hypercharge. So in this case, you're going to have a neutral boson, which is a mixture of these two. So it's different, but anyhow.
Just I have a question. When you say this mixing, you're talking about that rotation matrix we usually apply on the B mirror, and
Yes.
the other one to generate.
Yes, exactly. So because basically if you have a SU2 left symmetry and you can represent your model, your particles in a doublet, right? So you're gonna have like two times one or 1 times 2 vectors, right? Like so in the representation way. In this case, when you just open this derivative, this covariant derivative, you're gonna have by the way, you have an identity in the first one, right? In the partial one, and the other will be a matrix.
Yeah.
A matrix
2 by
like,
2.
2 by 2, exactly. So when you start to put the other terms inside from B, from the U1 symmetry, there, you're gonna have the contributions on the off diagonal and diagonal contributions. In the diagonal contributions, you're gonna have basically
I think I will
Yes.
talk about this.
Yes,
Yeah,
basically-
because
yes.
you're talking about
Sorry.
pre-symmetry breaking.
Yes, the construction of the symmetry breaking, exactly.
Yeah.
But yes, sorry. So basically what I mean is you have to take care when you show the image and what you have talked so far. I mean, you have to try to avoid to talk about things that you didn't dive deep,
because
you know?
I said it interacts with itself when it's
Exactly.
non-abelian,
But
and
you
here
didn't talk about the Z.
the Z boson.
So it's very intuitive for a professor like I like to say like Carlos Pires from the UFPB. He would ask, I am sure. Once you talked about the W, but you didn't talk about the Z, he would ask.
True.
You were right when you said that non-abelian gauge theory indicates that the gauge bosons interact with themselves. But the thing is that those bosons are not the same bosons that you get from the non-abelian gauge theory. Those are bosons you get after you break the symmetry.
Yeah.
So actually, if you get the W1, W2, W3, and you can have the final diagrams where all the three interact, but after that you have to be careful because, as Jessica said, the symmetry now, not the symmetry, but the charge that you care about.
It's a mixture. Because you're gonna have Q is equal to T plus 1/2 hypercharge.
Yeah,
It's just a matter of something you have to say.
Technical, yeah.
It's construction. Yes.
Can I ask a question? Can you go back to the internals, the gauge symmetry of the internal model?
Gauge symmetry. Okay.
Yes. So if the T1 does not represent a conservation of electric charge, so what is the charge that is conserved by this rule? What is the charge that represents this U1 there?
The charge of the electric charge, and the symmetry of U1 of electromagnetism gives me I can derive with these. I don't have exactly the equations here, but I can derive the conservation of charge, a conserved current, but it's just the electric charge because every interaction has a charge. Was that the question?
It's hypercharge.
Do you remember when
The generator, the
And the
The
charge, the conserved charge is the hypercharge of that U1. So as they said, when you break the symmetry, SU2 left U1 hypercharge, you get U1 electromagnetism.
Yeah.
Which the conserved charge is the electric charge. That's the one that you're talking about.
after
So-
symmetry breaking.
Huh?
After symmetry
After
breaking.
the symmetry break.
Mm-hmm.
So can I just so this
Mm-hmm.
is
Ah.
supposed to break, you get U1 electromagnetism, which you can say has the charge, which is the electric charge.
Just
So
change that A to a 3, please.
Yes, that 3, exactly. Sorry.
so this breaks and you got just SU3, which doesn't break. This doesn't break.
Mm-hmm.
Plus U1. And this get the electric charge. This is just hypercharge. Okay? This combination.
Yeah.
This equation that we are saying on the board is called the Gelman-Shishima relation. It relates the electrical charge Q with the charge
Hypercharge.
from SE2, if I'm not wrong, the 3, say either spin,
Mm-hmm.
and Y is the
Hypercharge.
hydrocharge.
Yes.
Isospin and hypercharge.
Yeah, so those are the generators of this group.
Mm-hmm.
And you have a combination of generators creating your electric charge, which is the symmetry after the break of the symmetry, right? What is the name? SSB?
Spontaneous symmetry.
SSB,
Spontaneous symmetry.
So it's exactly what I was saying. You have to be careful because U1 is never electric. The charge conservation you get from laser current is not about the electric charge. There's no electric charge at that level. Electric charge does not exist
Doesn't
at
exist.
the level of SU2, SU3,
Mhm.
SU1. You know?
At that time.
At that time, when that thing's happening,
And
and
the start of
you
the universe.
reduce asymmetry breaking, and you get electric charge. You have to be really careful when you talk about it.
When I write
Because if
this,
someone asks you,
when I write this,
everyone is electromagnetic. That's why we always write the
mm-hmm.
C, L, and Y, because it's not hard. It's also to remember that that's not the same thing. It's the same mathematics for the U1. It's not electric charge there. Be very careful with that.
Mm-hmm. Because I only talked like after symmetry breaking, and
Yes,
Yeah.
you built.
I didn't pay attention to these nuances.
Yeah, you built electromagnetism, but then you also have what we call UV field. Which
Mm-hmm.
is that.
But now, great.
Okay, thank you.
Thank you very much. Vai ter chamada lá pro Mikael?
Okay.
Já é essa.
Só chamada assim.
So now we're gonna have the second talk of the day, and now this time it will be Mikael, who will talk about non-abelian groups. And come on, it's take your time.
I'm a little nervous. Let me just set up the time first. So hello everyone. Good afternoon. So Heitor gave us a notion of what a group is, the conditions of a set of elements must satisfy to become a group. He gave an example of abelian groups and how we can use that in electromagnetism for the U1 symmetry. But I'm going to talk about now non-abelian groups. So I'm not going to actually, we prepared those presentations in a way that he didn't need to say what I was going to say, and I didn't need to repeat what he just said. So in this presentation, I'm supposed that everyone already knows the groups, what it means to a group to be abelian actually, and all those things. So we start the discussion by just saying what is a non-abelian group, given that we already know what a group is. Okay, so this is my last presentation as an undergrad student. Hopefully. So basically, there are two topics. I divided this presentation in two parts, just like Heitor did. The first part is going to be focusing on non-abelian groups in general. I'm going to discuss what is a non-abelian group, example of a non-abelian group, and I'm going to talk a little bit about isomorphism, because I'm going to use the example of SO3, and I'm going to use the fact that SO3 is isomorphic to SU2, and then with this I will skip to part 2, which is the applications of group theory and the electroweak sector. This is what we're going to do. First, a brief definition, of course. Just like Heitor said, in the groups, we have the elements and we have the operation. We define the elements and we define the operations. And within these elements, we have something that we call generators of a group. What is a generator of a group? The generator of the group, usually called also bases, are elements of the group in which we do combinations in them, and they can generate all the elements in the group, all the other elements in the group. So basically, if I have a generator A and a generator B, and if they are under a operation that is non-commutative, which basically means that if I take the commutator on them, it's going to be different than 0, and I have a non-abelian group. So this is the raw definition of a non-abelian group. It's a group in which I have the generators and they do not commute. Okay, an example of a non-abelian group, Heitor used the D3, the Dieter group. I focus in here on the SO3 group. Basically, the SO3 group is that group related to rotations on 3 dimensions, basically. I have this set of subgroup in the SO3. So, for example, if I fix the x-axis and I do a rotation around that axis, what I need to do is that I need to apply this transformation in here, in which I call Rx. And of course, if I fix the y-axis and the z-axis, I have something similar. Those 3 matrices are called the rotation matrices in 3 dimensions. And of course, the infinitesimal generators for this group that we just discussed are those 3, in which I called Jx, Jy, and Jz. And they obey this commutator relation in here. As we can see, just like we saw, if the commutator is different than 0, then it's a non-abelian group. In this case here, it's not only different than 0, but it's also cyclic, which means that if I take the commutator on one generator, 2 generators, that will be proportional to another generator belonging to that same group. So we say that it's a cyclic group. Why did I decide to talk about SO3? Because we have something called isomorphism when we're talking about group theory. And basically, I say, okay, I have this commutator relation in here. So do I have another group that has a commutator relation similar to this one? And actually we do. And it's the group called SU2. It's Pasch unitary. And the order of the matrices on this group are 2 by 2. And I think the best example we know from quantum mechanics, something that does not commute and it's also cyclical, are the Pauli matrices, right? I can take the commutator on the Pauli matrices, for example, sigma x and sigma y, and that will be proportional to sigma z. So that is an example of a non-abelian group, the Pauli matrices. They are 3 generators. Sigma 1, sigma 2, and sigma 3 are the 3 generators of this group. And why do we say isomorphism? Because sometimes people confuse isomorphism with if the group is isomorphic, then the group is the same. Well, they're not necessarily the same. Just like I said here, if those groups, they preserve the same algebraic structure, we call it isomorphism. What's the algebraic structure we're talking about now? The algebraic structure is basically the commutator. They have similar similar expressions for the commutator. So we say that we have an isomorphism between those two groups. Basically, this is the main idea in here. And of course, the generator in this group are the Pauli matrices divided by 2, which are just defined to be T. That will be similar to the T that we have in here. Of course, I decided to talk about this because now I'm going to talk about the second part of my presentation, which is the electroweak sector. Just like Jacinto wrote in here, the electroweak sector is basically represented by the symmetry of SU2, L is standing for left-handed, and U1, Y. What this Y in here represents hypercharge. So this is before symmetry breaking. We're talking about the electroweak sector. And this is very important because this is where everything comes together. Because remember I was talking about number of generators and everything. We will see that the number of generators is closely related to the number of gauge bosons in my theory. So in the SU2, I have 3 generators. Why? Because in the SUN, I have n squared minus 1 generator. So for SU2, I have 3 generators. And for U1, I have 1 generator. That basically gives me a hint that from this symmetry, I can have 4 gauge bosons. That's the main idea in here. And of course, this is a non-abelian group. I have, of course, a subgroup that is abelian, but I have non-abelian contributions from the SU2. So this thing as a whole is non-abelian. And why does it matter? Because in the next slide, we're going to talk about covariant derivatives. And this is very important because usually the gauge boson, when we're redefining the derivative, the gauge boson comes with the generator. So this is very important because what we have in the gauge invariance process, we have a Lagrangian. We take a look at what symmetry makes that Lagrangian conserved globally, which transformation makes that Lagrangian invariant, which global transformation. And then we promote this global symmetry to a local symmetry, and then we redefine the derivative from a simple derivative to a covariant derivative or total derivative. And for the electroweak sector, we usually define the derivative to be in this way in here. And here I have the covariant derivative equals to the simple derivative we have, plus those constants in here, and the coupling constant of the interaction. I have the gauge bosons, there should be a mu in here, sorry, and I have the generator. Just like I said, the gauge bosons, when we're redefining the derivative, they come with the generators in the theory. For example, the electroweak sector, we have this transformation for the derivative over here. And of course, this term here represents the SU2, and this term here represents U1. But again, I just need to make a quick comment. Just like our graduate students said, this is not the final gauge bosons we have in the standard model, because this bu mu in here and the W3, we have to do a combination with them to generate the Z and generate the photon. And of course, this is W1, W2, W3. Why? Because we have 3 Pauli matrices. So we have 3 terms in here, and we have 1 term in here, because this one here is with respect to the symmetry U1. But again, just as this quick comment, just like everyone said, this is not the final gauge bosons we see in the standard model. And this was the first example of using non-abelian group theory for particle physics. And another example, I think that's very convenient to talk about this one, is usually when we write down the Lagrangian for a vectorial boson. The Lagrangian as follows, as we already know, for a boson that has this spin 1 is this one in here. Of course, there's this cross in here because this term is not gauge invariant. But we want to focus on this tensor here, F mu, because this tensor is giving the complete formula for this tensor is this one in here. But take a look at something. Because when we're talking about electromagnetism and we know the electromagnetic tensor, there's no this term in here. The electromagnetic tensor is just this one. Why? Because electromagnetism is a linear theory, and this term here, in which we have the commutator, is a non-linear contribution. Electromagnetism is a linear theory, and also, just like Heitor said, I don't have photon-to-photon interaction. So this term here, we require this one to be 0. That's valid for abelian theories. But when we're discussing non-abelian theories, and I have interactions among our gauge bosons, then I have to include this term in here for the tensor. Basically, that's the main idea in here. And of course, just the main difference, just to summarize everything, the main differences, just like we saw, Heitor said, right? For the group U1, we usually to have a covariant derivative written in this way in here. We introduce the gauge boson, and here hidden, there is the generator, but the generator for U1 is just 1, which we already know, so it doesn't appear in here. And the generator of SU2U1 are the Pauli matrices, proportional to the Pauli matrices, and proportional to the matrix of the hypercharge. This is the first difference in particle physics when we're talking about non-abelian and abelian groups. The second one, just like we saw, in abelians, we don't have self-interaction between our gauge bosons, so we require this non-linear term here to vanish. But if we have terms that we have interactions between our gauge bosons, then I have a positive contribution from this term in here. I think I'll write something very quick on the keyboard. I'm sorry to the people watching online, but it's something that we usually have like this when we're studying particle physics. It's something like the generator. If I have G being the generator of the group, I have this expression in here. GC. If I'm talking about U1 symmetry, I only have one generator. So as we expect, the commutator, of course, must be 0. But for non-abelian gauge group, for non-abelian groups, this term is different than 0. And this term is here is called structure constant, I think, right? This term here is just the I, imaginary number. This is the structure constant, and this is the cyclic generator. I have this and this proportional to another generator belonging to the same group. And that's the main idea. An example of abelian groups, just like Heitor said, after spontaneous symmetry breaking, I have quantum electrodynamics. And non-abelian case, I have the electroweak unification, just like I was talking about. And of course, I didn't discuss about it, but we also have the strong force, right? Which is represented by the group SU3. That's it. That's the presentation. Thank you so much.
Quite nice. So do you see any physical implications for non-abelian theories?
I was telling in here, I think the most, which makes it clear for me, is that when we're talking about non-abelian theories, we usually have self-interaction between the gauge bosons. So this term here does not vanish. But for abelian theory, for example, electromagnetism, we don't have self-interaction because we have non-linear contribution. So photon to photon, there is no interaction photon to photon.
So that's why when we first studied gauge theory, we realized that the electrodynamics or the QED or the Maxwell equations, the AU, could not come from a non-abelian theory. Mm-hmm. So the starting point was an abelian theory because we knew that Maxwell equations hold. Yes. That's the starting point. And do you know why? Do you know why we need non-abelian theories?
Non-abelian theories. Why actually? I don't know. I know that we use, just like I said, we know interaction between the W boson self-interaction. So that will be a guess. why we need non-abelian theories.
I know, but what motivated us to go into non-abelian theories?
Non-abelian theories.
What was the driving force?
I have to be honest. I really don't know.
So just save that question and then later you can answer.
Okay.
Maybe I have a question, not just for you, but for everybody. I think it's a very simple question, but maybe it makes thinking. Why does the photon doesn't have an axial interaction? Why does the photon just have vectorial interactions?
Yeah, I want to know the answers to that.
Don't know.
But the others should know. So why the QED interacts with psi bar, gamma mu psi? And why is that?
The Hamiltonian of the quantum algorithm is very implementary.
Psi.
That's the question that I would make for him when you were talking. But I knew that it's very simple, but not that simple. I mean, it's simple because it doesn't have a term. So if you just studied, we even didn't, would not need to go to that discussion yesterday because you just need to know that the weak bosons, they are related to parity via the rule experiment. So if you knew this, you would have the answer, let's say. But to go beyond, you would need the discussion yesterday, I guess.
Yes.
To think about this question, perhaps you will need the discussion.
The discussion of why we need non-abelian.
Now, what is, I mean, we were discussing about parity, we were discussing about pseudo interactions in general. And pseudo interactions come from, for example, terms, operators that violates parity, for example.
The question that you referred is why doesn't have an axial form?
Yes, why we don't have a gamma 5? You remember that? In the case of photon, we have psi bar, gamma mu, psi, and then the photon. But for the case of Z and the case of the W boson, we have an axial a vector, a V minus A kind of interaction, which is gamma mu times, okay, I have to write, but the kind of interaction is like this one, like gamma mu 1 minus gamma 5. So this, and here we can have this guy, and here let's say the blue boson. So this is a prime, right? So this is the interaction that we are talking about, the axial interaction that generates this violation of parity.
I think if you're not familiar with relativistic quantum mechanics, in wave function or field, is to understand why gamma 5 is what makes it actual or pseudo interaction. And then you can maybe later look at a relativistic quantum mechanics Kreiner, or maybe even the chapter on PASCCO, and check that it's because if you apply the parity transformation on a spinor that is multiplied by gamma 5, you get a different result than you should get just from this. It's something you calculate and check it out. I don't know if someone has this.
Basically, it flips the sign of the field. But it's nice.
Okay, well now I inspired by this one. I'm gonna ask another one. So why can we have this interaction?
What's that?
Cease charge operator. Charge communication operator. Can we have this one? Lucy?
This one, no, this one you can't.
Why?
But this one you can.
This one I can?
Yes. It depends on the symmetry that you are assuming.
Okay, now I'm going to replace this guy, side. This is the side. I'm going to replace by the frame. Can I have this one?
I don't think so, because of the charge of the term.
But it's not the photon, right?
This is the photon. Yes.
Ah, okay, okay. So
But that's a
it
the
changes.
electron, right?
So there is
changes,
an
it
electric
changes.
charge.
So it changes.
Yeah, then you can, yeah.
Yeah.
This I can't.
I think so.
And this I can't.
Yeah, because you have like electric charge of this term.
You are not assuming a teaching particle that if you just
So I can or I can't?
I think you,
with that line.
no, let me
I
think.
don't think so.
So this is charge minus 1.
Of course,
Yes.
but the
This is
problem-
minus 1 plus 1 minus
minus
1.
one.
Yeah.
Okay, okay, but the point is,
Can I have it or not? No, because violet is charged, right?
yes,
Then I can have this one.
in principle, yes.
I think
Probably.
But I don't think so, because you would, in this case, you're gonna have a new, I mean, you're gonna have an additional term.
You have to check if
This guy will it will flip. It's, I mean, it will flip chirality. I don't know if it would, for direct Fermat, I think it doesn't work.
I don't think that term
Take a
is
step
Lorentz
back.
invariant.
Huh?
Is that term Lorentz invariant?
No, I don't care about Lorentz invariance.
But
No, this term is Lorentz invariant.
with but it flips the sign when you do
It
the.
doesn't matter. It will be Lorentz invariant.
It will be because you're gonna have the
I'm
bond.
compressing.
It will go
Whenever I'm
to-
compressing the indices, it will be Lorentz invariant.
It will get the let's say, the gamma 0 and the gamma.
But it's not related with Majorana particles.
Yeah, it's just in that direction.
If it's,
Because
if it's
because
a
I
direct,
think in that case it is not possible.
If it's a Majorana, it's not possible.
Yeah.
Okay, so if this guy was a Mariana particle, let's say it's the neutrino,
See.
that
Yeah,
seems
it
to Mariana,
doesn't
so
work.
it's not possible?
No.
Why is that?
same,
Say what? What's the reason?
the same discussion, but now you would need the bar.
Because the particle is
I think in that
It's
case,
all like
in that
particle.
one.
you don't have an interaction term.
It's,
This is the level.
no, it would be a.
So if this is
Majorana
the
particle.
example, neutrino bar C neutrino, can I have this one? Let's say it's not the photon, this
Yeah,
is like
no.
some Z prime.
This one you cannot have.
This one you can,
I can have this one.
I think
I don't
you
think so.
can,
you can
you
have.
can do that.
Because the charge conjugation on a particle.
You can have it because basically
have
it
this
will
one?
flip. Let me ask.
I think so.
In this case, if it's a Majorana particle, you can have it because it will flip the chirality, but the chirality basically.
I'm not even opening up the chirality.
No,
I already
okay, it's
suppressed
okay,
it.
but then it
This
will not
guy
change.
has chirality
It's
inside.
its own type part. Okay, its own type part.
Because we write like this, right? I don't want
Yeah,
it
perfect, perfect. But
But in
Anyhow.
that case, you are not assuming a standard model neutrino. You
No,
are
no,
assuming a neutrino because
This
standard
is the
model.
standard model neutrino. This one and this one. Can I have this interaction or not? This is the neutrino, the active neutrinos. Can I have this interaction?
I think you're gonna violate lepton number.
Lepton number minus 1, plus 1, minus 1. So it's minus 2. So that expression violates lepton number, right? Okay, so I couldn't have it because it violates lepton number.
Wait.
Well,
Whatever,
if my
if you
model
want-
conserves lepton number,
Yes.
if my model conserves lepton number, it doesn't have to.
But it depends the symmetry you are working with.
That's it, yeah, if my model. But now I'm saying now I have this.
That
Can I
Dark
have
photon,
This is a photon.
just a photon. You can't.
Can have,
It doesn't have charge.
it doesn't have electric charge, right? All right, and now can I have this one?
Also,
Okay.
no, because
Why
this
doesn't
guy
have charts?
is not even charted under a standard model. In principle, this guy is a single.
Okay. And can I have this one?
No, you can't. If it's a Majorana particle, you can't.
You
The
need
same
to
reason.
see there.
Today was the I think I received 10 calls today.
I know, this is the discussion
Calls
that you
you.
had in your.
No.
No? This was.
No, it's
So
not.
it's the same discussion.
That was a Rukawa. This is a vector.
But that's the same discussion we had. Yes.
So I can't have this one.
Is that a Z or a Z prime?
Z prime.
Z prime.
New interaction.
You can choose the.
Can I have it or no?
I think so. Maybe depends on the symmetry.
Yes, I can. Can I have this one?
Again, depends on the symmetry. I think so. Because
It's, okay, okay. No.
Can I have it this one or not?
I think in this case it enters the standard
Is
model.
there something that prohibits it?
I think it will be like one. If it's the
No.
standard
No.
model.
I think you can. It
Yeah,
depends
so
on
I
the symmetry.
in principle I could. I mean, depends on the model or what, but there is
Okay,
nothing that
I see,
prohibits
I
it.
see. Yeah. Okay.
Okay, fine. And can I have this one? And let me just block this number because it called me like 100 of times. Let me block. Can you block this number to me? This first one did. Can I have this one?
Without the notion?
The mass.
Can I have it?
Yeah, you can.
Again? In principle? This sigma is some scalar, correct? Can I have like this? Is the mass like this?
Yes. The game is starting to be familiar. So
Can I have it or not?
yes.
And like this.
You need that. You need.
Redefinition.
In principle, yes. In principle, you can.
And like this.
No.
No? So you're saying that wire hanging machines cannot be
You can.
directed?
You can.
I think it
Yeah,
depends,
because
no?
they can be.
I
They
can
can.
have
They can be direct.
Wait, is that like because it's not a drag?
It is. Now it is.
Yeah, that's the point.
Now
he's just
it's
joking,
not.
like
If you have the-
he's just like playing with the
I'm confused right now.
scalars. You have
I'm just
like
putting on my
if
mind and
if
asking
this guy
what
like
is
this
possible
way, you
now.
have to see that it's Dirac or Majorana, and then you have to say first you have to ask
okay.
yourself it's a Dirac or Majorana.
I'm just asking whether it's possible or not.
Let me
That's all.
finish the presentation here.
So I can have this one, yes, as long as the neutrinos are right, are direct neutrinos.
Bye bye, guys.
And I can have this
We
one.
will continue discussing here.
As
Ciao,
long as
bye.
neutrinos are Mariana neutrinos. Can have both.